Hello and welcome to the second video on proof. Today we're looking at proof by contradiction. The usual exam question will give us a statement, a proposition, and ask us to prove that it is true by contradiction. Our proof follows 4 steps, 4 stages. Step 1, we assume the statement is false. Step 2, we reason logically from our assumption until we come across a contradiction, something that is not true, which means we've arrived at stage 3. Step 4, we state our assumption must be wrong, which means the statement, the proposition, must be true. I'll take 3 examples to show you how it works in practice. Here's our first. Prove there are no integers p and q for which 12p plus 21q equals 5. Step 1, we assume the opposite is true. We assume there are 2 integers p and q for which 12p plus 21q equals 5. Step 2, we take our assumption as our starting point and reason logically from there. Now if 12p plus 21q equals 5, we can factorize the left-hand side and then divide by 3. Which gives this. As p and q are integers, the left-hand side must also be an integer. But the right-hand side, 5 over 3, is not an integer, it's a rational number. So the left-hand side cannot equal the right-hand side. One side is an integer, the other side is not an integer. We have a contradiction. We've reached step 3. Step 4 is where we say our assumption must be wrong and the statement must be true. Here's our second question. Prove there are no positive integers a and b, where a is odd, such that a plus 2b equals the square root of 8ab. Step 1, assume the opposite, that there are 2 positive integers a and b, where a is odd, such that a plus 2b equals the square root of 8ab. Step 2, we begin with our equation. A natural thing to do is square both sides to get this, and then multiply out. Collect terms on the left, and we have this. And we should spot this factorizes to give this. Then we can take the square root of both sides, which means a equals 2b. And that means a is an even number because b is an integer. But our assumption states that a is odd. We have a contradiction. We have reached step 3. All that remains is to say our assumption was wrong and the statement must be true. Here's our third question. Before we start this, let's make sure we're clear on what is meant by rational and irrational numbers. 0.6 is a rational number because it can be written as 3 over 5, and crucially 3 and 5 are both whole numbers, integers. -7 is rational because we can write it as -14 over 2, and again -14 and 2 are both integers. Irrational numbers cannot be written as a fraction where both numbers are integers. Numbers like pi, the square root of 3, the cube root of 4, and e. These are all irrational. Back to our question. We're looking at the sum of a rational number and an irrational number. It would be helpful to call the one x and the other y, and the sum of the two z. Step 1, we assume the opposite, that there is an x and a y where the sum z is rational. X and z are both rational numbers. We could use a, b, c and d, but to make things clearer, I'm going to say let's write x equals integer 1 over integer 2, and z equals integer 3 over integer 4. We know x plus y equals z, which means we can write this. And if we make y the subject, we have this. Here we're subtracting 2 fractions. So we can put them over a common denominator and we get this. Now, take a look at that denominator. If we multiply integers, we get another integer, And look at the numerator. If we multiply and subtract integers, we get another integer. So we could write this. That states that y is a rational number, which contradicts our assumption. We have reached stage 3, a contradiction, and we take the last step. Our assumption must be wrong, the statement must be true, the sum of a rational number and an irrational number is irrational. That's it for this video. I hope you found some of that helpful.